Hi, in this segment we're going to talk about how to use singularity functions to construct the shear force diagram and the bending moment diagrams. There are several methods that are used to construct both the shear force diagram and the bending moment diagrams. However, the singularity function is a little bit more systematic and mathematical, so we're going to kind of pursue that and use it for an example in this section here. So I'll first define what we mean by singularity functions and then move on to an example. So the singularity functions are functions that represent concentrated loads or moments. So if we define, let's say, the x-axis and the y-axis to represent the singularity functions, this is an x-axis, for example, then I'm going to show a number of the singularity functions and how they are obtained from one another underneath here. So this is x-axis, and the y-axis is going to represent the graphical representation of the function itself. So if I look at the first singularity function concentrated at a point on the x-axis, we can represent it as a concentrated moment or a doublet. So this concentrated moment is equivalent to two forces that are separated by a very short distance. So we don't represent the forces, we just represent a circle with an arrow to show that there is a concentrated moment. And the mathematical representation of this so-called doublet, because it's a doublet of forces, is bracket x minus a to the power minus 2. So this point here is x equals to a at this point. So the location here is a at every point in here. What is the meaning of this? It's just a symbol that means that the function does not exist anywhere if x is not equal to a. So there's nothing anywhere. But at x equals to a, it's a plus or minus infinity at x equals to a. So that's kind of the definition of the singularity function of a doublet. It's symbolic. So whenever we see x to the minus a to the power minus 2, we would say that there's nothing anywhere except at x equals to a. Then I have two opposing forces within a very, very short distance such that their moment together is whatever is at this point in here. The value of the moment is right there. Now, if I integrate, we know that the one function can be obtained from another. So in this type of mathematics, the doublet can be integrated, and if it is integrated, it gives us a concentrated force or a concentrated value of the function that we can call a delta function. So doublet, when you integrate it, gets a delta function. And then if we integrate the delta function, we get a unit step function. And finally, if we integrate a unit step function, we obtain a ramp. So this is the hierarchy of discrete functions that are used to represent forces and moments in beam theory. So let's go back to the doublet and integrate it and see what would result when we have the integration that we have a delta function. So underneath here I have the integration of the doublet would give me a delta function. Delta function means 0 everywhere and then goes to infinity and then comes back to 0. So the integration, again, the meaning of this delta function, mathematically, we're going to represent it as x minus a to the power minus 1. And it means that it is 0 everywhere at x is not equal to a, but it is equal to plus infinity at x equals a. So again, this is just an interpretation of the delta function. That is 0 everywhere and it is equal to infinity at x equals to a. And mathematically, the form that we use is x minus a to the power minus 1. So if we integrate one more time, we would get the unit step function. Unit step function is 0 everywhere up to this point a, and then it becomes 1. So the value of the function is 1 at x equals a. And therefore, the unit step function is mathematically represented as x minus a to the power 0, which is equal to either 0 when x is less than a, or 1 when x is greater than or equal to a. So that in this case, the unit step function is the integration of the delta function. And finally, if I integrate the unit step function, I get the ramp, and the ramp here is mathematical form of the ramp is x minus a in brackets raised to the power 1. And it means that below x equals a is 0, and above x equals a it is equal to a linear function. So this is just kind of how we use the mathematics to represent the various forms of the singularity functions. Let's move on to now see how it's applied. So if we look at the applications, then basically note that if I integrate x to the minus a to the power minus 2, if I integrate this, all what I have to do is change the power from minus 2 to minus 1 and do an interpretation. So the interpretation of this is that it is 0 everywhere except at x equals a, and it's a concentrated load basically. If I integrate x minus a to the power minus 1 by integration, I get x minus a to the power 0, and this is a step. So this the form that results is a step. If I integrate a step to the 0 by integration, it gives me x minus a to the power 1, and this is a ramp. So you go from doublet to a delta function, and from delta to a step, and from a step finally go to a ramp, and then beyond the ramp then you have just very standard mathematics. So if I have x minus a, for example, to the power 1, if I integrate this dx, I use just simple integration, which gives me x minus a to the power 2 divided by 2. So these are the steps that we use, and here's a summary that you can see for that summarizes what we were discussing so far. So if you have a concentrated moment, a unit doublet, the expression is x minus a to the minus 2 equals 0. For x is not equal to a, and it's equal to plus or minus infinity to x equals a, and if you integrate it, you get now the unit impulse, which is a delta function, and the unit impulse, when you integrate it, you get the step, and the step when you integrate it, you get the ramp, and the ramp, when you integrate it, you get a parabola. So these are all different implementations of the singularity functions that can handle concentrated loads. So now to understand why we use singularity functions, we're going to apply it in an example where we have a combination of concentrated loads and distributed loads. And that's the beauty of the singularity functions, that they can handle concentrated loads, concentrated moments, distributed loads, and also they can give us the reactions without having to go through this step to find the reactions before we do the analysis. In the previous methods that we learned, we had to first find the reactions, taking moments and doing equilibrium, and then after that, then we can construct the shear force diagram and the bending moment diagrams. But here we can use singularity functions directly and determine the reactions and the unknown moments and the diagrams all together using the functional forms that we discussed. So let's see a concrete example to see how that works in practice. So here we go back to the previous example that shows us we have two concentrated loads, one load at 200 pounds and then a load at 100 pounds. And the first one is 4 inches from point O. The second one is 10 inches away from the origin O. And we have reactions R1 and R2. We have done this example before, just using equilibrium. We found that the reaction on this end is 210, on this end is minus 90, as you remember, and we used the integration to get the area under the curve to get the moment diagram as 3 straight lines. So let's see how we would do the same task using singularity functions. First, I write the distributed force, the force distribution that I see here. I have R1, 200, 100, and R2. So the Q is these 4, and the V is the integration of the Q, and the M is the integration of the V, simply. So if I write equations for Q, I integrate it, I get M, I get V. I integrate one more time, I get M. So if you see here, Q, I have R1, and R1 is an impulse, so the power is -1, so it's X, and the location is at X equals 0. So X equals 0 location, then the function would be X minus 0, which is just X, to the power -1. So this means impulse located at X equals to 0. It's positive, and the magnitude of the impulse is R1. So when you have R1 times X to the -1, that's a complete representation of the impulse located at X equals 0. And then we have also the force, 200 pounds, and it's going down, so it's -200, located at 4, and its impulse, so it's to the power -1. And then we have the force 100, so it's going downward, so it'd be -100, located at 10, and the nature of the force is that it's an impulse, so the power is -1. Finally, we have R2, located at 20, and it is an impulse, so it is raised to the power -1. Now the integration gives V from Q directly. Every -1 becomes a 0. -1 becomes a 0. And nothing else changes because we just integrate the impulse, and the impulse becomes a step. So I know that this is a step, this is a step. Every one of these 4 functions is a step. The location of the step where it rises, like that, This is at x equals 0, which is the location here. Then at x equals 4 would be the location for this, and so forth. So that's kind of the interpretation of the, the steps. And then one more time we do integration of the step. We raise the power. That's nothing else than raising the power to represent the step. Becomes, this is a ramp. And the ramp, the interpretation of the ramp is that it is turned on at a point, and this point is x equals a. So here a is equal to 0, here a is equal to 4, here a is equal to 10, and here a is equal to 20. And therefore we have a bunch of ramps, like 4 ramps, that come from the integration that we did. So if we just now represent the solution, you see that I have 2 unknowns in the solution. I have R1 is unknown and R2. And I have 2 equations, one for V and one for M. So we note that at x equals 0 minus V and M is equal to 0, and this is kind of redundant information because we know that. But if we consider V and M at x equals 20 or 20 plus, it means just a little bit outside of 20, then they should also be 0 because the beam now has ended, and then we don't have a moment or a shear force. So we're going to apply this condition. We set x equals 20 in these 2 equations, and use the condition that v equals 0 and m equals 0, and solve for the 2 unknowns that we require here. So we do that. At v is equal to 0, at x slightly larger than 20 inches, then if you look at the equation, I have here R1. So if I look at here, this is a step. It means any point greater than x equals 0, the value of the function is 1. So which means that R1 times 1. And that's what I got here. R1 times 1 is the first term. The second term is at any point that has x greater than 4, the value of the function is 1 again. And since 20 is greater than 4, then the value of the function will be 200 times 1, because that's the value of the step function at any x greater than 4. And that's what I have here on the second line. So I have 200, and then I have 100 and R2, and that is equal to 0. And I can do the same thing now for the moment equation. And note that the moment equation has ramps. So the ramp has a value at x equals 0, when x is greater than 0, and it has a value when x is greater than 4, has a value when x is greater than 10, and this has a value when x is greater than 20, which means that they all exist. So therefore I have R1 times x, and x is now 20. So it will be R1 times 20, which is the first term. And here I have 200 minus 200 times 20 minus 4. And that's what I have here, 200 times 20 minus 4. And I do the same thing for the last 2. The very last one, R2, doesn't give me a contribution because x is equal to 20, so it gets 0 here, contribution. Solving these 2 equations and 2 unknowns gives me R1, 210, and R2, 90, exactly as we discovered from the simple solution that we developed before. Now I have another example on singularity function that combines additional distribution is a little bit different. So in this example, we will have one concentrated moment, which we didn't have before, and we're going to have the loading would be a combination of concentrated forces, which we can represent as impulse functions, and distributed load, which is a step function. So the distributed load is a step function. The only thing that we want to point out here is that if you have a concentrated load over a segment of the beam, not the entire beam, then you have to represent it using two step functions, as I'll show you in a second. Yeah. So before I start this example, I wanted to point out that we can represent the impulse in a different way. Let me just clear this page here. If we have a unit step function that is turned on at a point and turned off at a point. So at x equals a, you have a value of the function equals 1, and then it goes on until it turns off at x equals b. So in this case, you can say that this is the difference between two step functions. You can represent it as x minus a to the power 0, because that's the step function, minus, so this is turning on. Now you turn off, it will be minus x minus b to the power 0. And the difference here is actually the total function. So that difference is this will turn it on and this will turn it off. Okay, so that's, so if you have a distributed load that is distributed between 2 points, you can always represent it as the difference between two step functions. The same thing for a ramp, for example. You can have a ramp that goes like this, and then you want to kind of turn it off. So when you turn it off, then it continues as constant. So at x equals a and x equals b, then this will be the difference between two ramps, x minus a to the power 1 minus x minus b to the power 1. That means that the ramp is only operating in a segment on the beam, as you can see in here. So with this, I think we can now try to find a way to deal with the new problem that we have, since we have a combination of loads, as you will see here. So the problem that we have is that I have a beam, and the beam has it's a cantilever beam, and it has a concentrated end moment on that one end, and it has reaction R1 and a moment M1 on the other side, and these are unknown. And we have a distributed load between B and C. We have a distribution here of a load at 20 pounds per inch. And we wanted to find the V diagram and the M diagram using the singularity functions. So what we will do is we're going to represent the Q first. And the Q, as you can see, will have two doublets in here, and then one impulse, and then a unit step function that is represented over a finite segment. So once we identify Q, then by integration we get the V. By integration we can get the M, as you can see in here. So we represent Q as two impulses, two doublets. A doublet at x equals 0 and another doublet at x equals 10. And the kind of negative doublets from the sign convention that we have a doublet here, it's a negative, and then another one is in the same, so it's counterclockwise would be negative. So this is negative and this is negative, and therefore I have minus m1 times x to the minus 2 minus 240 times x minus 10 to the power minus 2. And then in addition to that, I have impulse at x equals 0, and the magnitude of impulses are 1. And then in addition to that, I have the unit step, the step function, and now the on and off idea that we discussed. We have, this is the on idea, and this is the off idea. So we have minus 20 because it's going down. It's downwards, the gravity is going down, so there's a negative q. The positive q is right here, but this is negative q, so it's a negative going down. You can see here, minus 20 times x minus 3, and then you just turn it off at x equals 7. So this is the most important line that we have here. Once we have the line figured out, then we integrate. So the integration, the minus 2 becomes minus 1, another integration becomes 0. Minus 1 becomes 0, another integration becomes 1. The 0 becomes 1, another integration becomes 2, and you divide by 2 because it's just like a normal integration in this step. And the same thing here, the 0 becomes 1, another integration becomes 2, and you divide by 2. And finally, we have minus 2 becomes minus 1 becomes 0. So now we did all of the integrations with the unknown parameters m1 and r1. We have two unknowns and two equations, and the two equations are equation 2 and equation 3. So again, we in order for us to get v and m, we take it, we notice that if we take x slightly larger than 10, in other words, we just put x equals 10 and understand the meaning of each one of these functions. For instance, x to the minus 1 would be an impulse, and therefore it should have a 0 value. But x to the power 0, it should be a step, so its value is 1. Once we do this interpretation, then everything is easy, and then we solve these two equations. You get these two equations here equals 0, and you solve the two equations and two unknowns to get r1 and m1, and that is complete determination of the solution of the problem, and hence we can now build the shear force diagram, as you can see, and the bending moment diagram. We have minus 160, a ramp up to this point, and then from this point to this point is a parabola, and then there's a step beyond x equals 7. So with this example, we are now able to utilize the singularity functions in building the shear force diagram and the bending moment diagram, which we will later on in the next chapter use it as input to do further integration and find the deflection